Hey everyone, how's it going? Thanks for attending. This is Breaking Chains, Hacking Android Key Attestation. That's me, I'm Alex. So I'm a senior red team engineer at Amazon. Spend most of my time performing threat emulation campaigns as well as security research. Also, here's my socials if anyone wants to connect after this. So today we're going to kind of go over a background of this research, sort of the primitive and kind of what got me looking into Android key attestation. We'll do a deep dive into what is Android key attestation, so you'll hopefully walk away with a better understanding if you're not familiar with it, as well as looking at an interesting bot fraud and abuse case that my research target was basically facing and using Android key attestation. We're going to dive into some common PKI issues, which are themes that you might be familiar with. We'll kind of highlight them and talk through what they look like in sort of like an HTTPS or browser implementation, and then we'll dive into the sort of like uniqueness of how those types of issues surface in the Android ecosystem. And then I'll talk about a certificate extension PKI issue that is particularly interesting that I have found across multiple implementations that are a result of the library that's actually vended by Google. We'll do a root cause analysis for how these bugs are manifested and wrap everything up at the end. So a little bit of background. Basically what got me looking into Android key attestation. So I had a research target kind of come across my desk, if you will, that was facing an interesting bot fraud and abuse problem. So they basically think about it this way. There's a Android client app where users are basically competing in a offer-based system. So you launch an Android app, you get a list of offers, you're continually refreshing, you're basically racing other users of the application to try to claim an offer in the service. And naturally, if anyone's familiar with bot fraud and abuse in the past, this is like the perfect recipe for gamification of that type of system. And very quickly, what we found was the creation of bot service providers who are, writing Python scripts and anything, running them in different cloud service providers' VMs, basically to beat out all of the legitimate users who were trying to claim offers. And what we found was it actually tipped the scale so bad that a legitimate user couldn't use this service without paying for a bot service provider. They completely gamified the entire system. How the research target looked to basically to combat this issue was implementing Android app and key attestation, with the idea here being if we can attest the mobile clients that are interacting with the backend service, will raise the barrier of entry and that sort of threshold for bot service providers, where they'll have to have a physical mobile device to interact with the service. Now, this won't obviously completely drive bot fraud and abuse away, but again, hopefully lifting that barrier of entry to where it kind of becomes not profitable for a bot service provider, right? Like if you do things like limiting a session 1 user per device, then like a bot service provider would need to literally buy hundreds of devices and basically have a full device farm, which again, not impossible, but hopefully raising that barrier of entry. One of the interesting things we found very quickly was with the implementation of Android app and key attestation, there was a very huge disruption, right? Like we saw everything looked great, bot numbers going down, but what we found in the oncoming weeks was the profit margin was still there to where bot service providers were actually, we basically created a 0-day market for Android key attestation. Bot service providers were looking for all the ways that they can basically circumvent the implementation and continue to do bot things. So in an attempt to combat this, I dove in, spun up what we like to call like a fraud security campaign. So we take the concept of a threat emulation campaign, and we'll just go try to emulate the threat actor, in this case being a bot service provider. So naturally, we go and look for 0-day vulnerabilities ourselves. So what is Android key attestation, if you're not familiar? The first thing to clarify is it is not app attestation. They're commonly conflated terms that are used incorrectly and interchangeably when they shouldn't. So as an overview, app attestation is, you may be familiar, you might have heard of like the Legacy Safety Net API or the Play Integrity API. And really what app attestation does is just ensures that the version of the app running on the mobile device is the one that's in the actual Google Play Store. There's also some built-in safety mechanisms that, like some rudimentary rooted device and bootloader checks, some anti-hooking and swizzling checks for anyone familiar with like Frito orchestration. And ultimately, this is all achieved by a verdict that is issued by a Google API off device. It returns a JOT. You validate the JOT in your backend service. Everything looks good as long as it meets your security requirements. The difference here with Android Key Attestation is Android Key Attestation actually is just verifying that a key pair that is created and used by the app is stored in secure hardware on the device. So there's some protections there that ensure that it can't be extracted from the device, specifically the Android Keystore. And the main difference being if we're looking at like the actual credential material that's being produced, Android Key Attestation actually uses PKI and generates an X509 certificate chain that is attesting the key pair generated by the app on device, and it's up to the developer to validate that off device. The device sends it back to a developer-owned backend API, and they validate the X509 certificate chain and the verdict. So diving a bit into the Android Keystore, this is where your key material is actually stored when you are using Android Key Attestation. There's two main types of secure storage on Android devices. There's the what I'll call like more legacy implementation, which is the trusted execution environment. This is obviously like pre-shipping crypto chips and hardware security modules on Android devices. It's a containerized ecosystem that utilizes the ARM trust zone. There's a completely separate operating system. If anyone's familiar with Android open source project and the builds, Google has the TrustET OS. It's the completely separate OS running in this container. There's a series of libraries and user space libraries to do basically IPC to communicate with this secure environment. And the sort of future, if you will, is called the secure element. This is your completely separate hardware security module where, you have like a completely separate crypto chip that's using a serial interface basically to store secrets. And kind of reiterating, the two main security protections here is that it prevents key extraction off of the device. The cryptographic material never leaves secure hardware. You actually are interfacing with an abstracted API. You never get to touch the private key material. You're just sending IPC messages and basically sending like plain text with a pointer to a key into the environment, and it's just spitting out the ciphertext essentially. And one of the other really cool protections is it has key authorization, so you can scope keys to make sure, like, I have legitimate app A, I can't write illegitimate app B and steal and use the keys from app A. Quick overview of what PKI looks like in this environment. So there's obviously no certificate authority. Essentially, Google distributes key pairs to manufacturers. You can liken this to like the key marrying procedure for actual certificate authorities and like a HTTPS implementation. So Google gives these key pairs to manufacturers like Samsung, and at manufacture time, they actually inject the key pair into the key box on the device. And then when a developer wants to use Android Key Attestation, there's a Keystore API that in their app they'll use to actually instantiate, create key materials, key pair, and it'll use the key pair that was injected at manufacturer time. A common implementation of how you would see this, kind of abstracted, is once a key pair is generated inside of a device, since the private key is stored in the secure environment, what app developers will typically do is they'll sign sensitive requests with this private key pair. Private key never leaves the device, so it can't be man in the middle or stolen. Similar concepts to what you find in like WebAuthN and FIDO2 implementations. So how do you actually verify these hardware-backed key pairs? So as I mentioned, there's an X509 certificate chain. So you would follow standard practice. You would want to verify the chain of trust, making sure that the root certificate is signed by Google, each certificate is signed by its predecessor. The kind of common knowledge of PKI validation. There's a certificate revocation list, just like in HTTPS implementations. We have instances where key pairs get compromised. Google maintains a list you want to check, obviously, to make sure that none of your attestations are being signed with compromised key material. And then once your X509 certificate chain is validated, the important part of Android key attestation is actually within a custom OID extension that is in the leaf certificate of the chain. The scheme is a little small on this screenshot, but we'll cover it coming up. But this is what gives you all of your interesting information about the device, right? Is the bootloader locked? Is it a trusted execution environment, implementation, secure element? How are the key pairs stored? Well, as long as some other like patch level metadata. So diving into a little bit more about what the X509 certificates look like, here's some decoded certificates. Specifically, this is a leaf certificate and the decoded attestation extension, which kind of has some of that schema data from the previous slide. So again, reiterating, so this is like 3+ X509 certificates in the chain. Typically, this is like a root, an intermediate, and a leaf. You have that leaf certificate that has the custom OID extension with the attestation data. Also worth noting, there's a very interesting OID extension on the intermediate certificates. They actually increment the number of certificates that are issued by a device. This is a really good fraud signal if you have a validated X509 certificate chain. So if, let's say, a threat actor does find a way to defeat the Android key attestation implementation, and they're using a single device to mint multiple certificate chains and key pairs, this is where you would kind of see that signal on the back end. So previous public research. This, as most security researchers probably know, the first thing you're going to do is look for the shortcut to the answer. And in diving into what previous research was done on this, this is kind of what I discovered. So pretty much all the research in the past has been specifically targeting the trusted execution environment in Android devices, and really not even within the context of Android key attestation. So there's some really interesting research done. There's more out there, but these are kind of like the top ones that I found that had the most material. But there were some really interesting Samsung Tigris vulns a few years back, as well as a really good presentation at Black Hat 2019 called Breaking Samsung's ARM Trust Zone, where they found some really cool memory corruption vulnerabilities in the user space IPC library, and they were actually able to read the memory inside of the containerized environment for the trusted execution environment. So this kind of gives you that exploit primitive where if they were targeting Android key attestation, they could actually read that key pair that's injected at manufacturer time by or from Google. They could actually read that out of that and compromise the key pair. So then it would be valid until someone catches them and it ends up on a certificate revocation list and it's patched. Another interesting kind of tidbit about research in this area is the custom ROM community. If anyone runs their own custom ROMs in Android, you might have dealt with issues with the Google Play Store. There's some really interesting tooling and discussions about using compromised key boxes and tools to flash your own custom key boxes for your custom ROM implementations. Those were super helpful with this research. Not much in the secure element area in terms of circumventing the new hardware security modules. But there was no information at all about actually just breaking the PKI trust model, which really is the low-hanging fruit here, right? Like, who wants to go have to find crazy dank ODAs for memory corruption vulns in the Android operating system when you have this fragmented and disparate environment where we're basically telling developers, hey, go do one of the hardest things in crypto, roll your own validated X509 certificate chains, and also good luck. One last piece of context before we dive really deep into the research is the specific research target that I was looking at. This is speaking a bit to how they were actually using Android key attestation. So this is what it looked like. Basically, a user would log into an app. The app would create a key pair and attestation certificate. They would send the cert chain to the validation server. If the certificate chain was validated and everything looked good, the server would basically return a pointer to the public key that was being used on the back end to validate signatures, and they were using a HTTP message signature RFC basically to sign the sensitive request to the back end. Again, the whole primitive here being there's a private key that no one can touch, only the legitimate app making the assumption that app and key attestation are working, and every time we see a correctly signed request, it's coming from a real Android device. So here we'll dive into the beginning of sort of this research in terms of highlighting these common PKI issues. So there's 3 common PKI issues. 2 of these you're probably familiar with if you've ever looked into any custom PKI implementation, and then 1 that's unique to the Android environment. So there's a certificate chain of trust that you would always validate. There's a certificate revocation list, again, in all PKI implementations, this would probably exist. And then there's a unique hard-coded certificate, one that we'll talk about, that's really unique to Android. So for validating a certificate chain of trust, again, this is like a PKI 101 class, if anyone needs to pass an interview question on how PKI works. But this is one of the first things that you look at when validating a PKI implementation. So this is really establishing that chain of trust in an X509 certificate chain. So making sure the root is signed by Google with the key pair we already talked about. It's injected at manufacture time, each cert signed by the predecessor. But really how we test this in an Android key attestation implementation is we basically want to interact with the developer's backend server that's validating chains to figure out if they're doing it correctly. And how we sort of orchestrate this type of test and testing for the certificate chain of trust is pretty easy. It's actually the same way that you would do it if you were looking at a HTTPS implementation. You can literally just generate a EC key pair using whatever tooling you want. Could be OpenSSL CLI, could be Python code, choose your weapon. But you'll generate an EC key pair that's not stored in the trusted execution environment or the secure element, just reiterating that's the real crux of this research here it's can we find a way to get our hands on a private key and basically spoof the attestation to say that it's in the Android Keystore when we actually have our access to it, so we can write a Python script to interface with sensitive APIs and such. So you'll generate an EC key pair, not stored in the T. You'll create a forged X509 leaf certificate, embed the public key into that certificate, and then we'll forge an OID attestation extension and say, yeah, I'm in secure element, super safe, unique nonce, everything's patched, we all look good. And you literally will just tack that onto the end of a legitimate leaf certificate and throw it to a backend developer's API. Here is some code for ants that's kind of hard to see, but it's really just doing exactly what I mentioned. We're creating private key, creating a custom certificate, forging attestation data, and sending it. The screenshot all the way on the right, you can kind of see, hopefully, there's basically an attestation post request body parameter that you're just sending each of the certificate chains in an array to the backend server. And then just using that same logic again, we're just going to take that key pair that we actually have access to sign our sensitive request and send it. And one of the funny things that I found with diving into this was this actually worked. On our research target, they weren't, there was an off by 1 error, and they were only validating certificate chains up through the intermediate certificate. So that was a fun one. So now, certificate revocation lists and how you would test those in Android key attestation implementation. So again, they work just like anyone familiar with one. They work just like an HTTPS one. So we're just basically looking for anytime a key box is leaked from a manufacturer, which happens way more than you would hope. Google basically just maintains a list of all those compromised keys, and we expect developers to basically check the list and make sure that none of the compromised key pairs are being used with that. This kind of exploit primitive works exactly like the last one, except this one's, I'd almost argue, a little easier because you don't need to write code basically to generate your own key pair. You really just need to go Google, join a few Telegram channels, and get into the custom ROM hacking community to find the latest leaked key box. And you can see, like in the bottom right corner, here's one leaked from the Nubia manufacturer that literally it just has the EC private key there that you can use to forge your own chain and send it to see if they're actually testing or validating against the certificate revocation list. So this last of the common PKI techniques is a little unique to Android in that this is testing for hard-coded certificates. So just a little bit of history on Android key attestation. Pre-Android 7, there was no hardware attestation support. Like many things in Android, it's a fragmented environment, and things roll out It takes many years and many iterations for them to be fully rolled out. So what you found was really this interesting kind of stopgap solution where they call it a software-attested key pair, which basically just means it's like in memory, like it's not actually stored in a key store or anything. So one of the easiest ways to test for this is to literally just go look at the AOSP source code, and the private key pair for the TrustDT operating system, which is what gets shipped with all AOSP builds for Android phones, is just in the source code. So same concept as the certificate revocation list technique. You will just take that private key pair, mint a X509 certificate chain, and sign it with that key pair. So you can literally forge the whole chain from root to leaf. One particularly interesting thing with this method is this works way too often, because if you're a developer, how do you test how do you actually like do end-to-end testing for your app that's using Android key attestation if you must use a physical attested device? Like if anyone's ever like tried to circumvent app or key attestation, like this would basically imply that the developer would need to like have a working FRIDA orchestration, certificate pinning bypass, and all these techniques that you would do with like mobile app testing to literally just like do integration testing. Doesn't work. So what they often do is they actually allow list hard-coded certificates in pre-prod environments. And if they're not restricting that to pre-prod environments, you can just basically use the hard-coded certificates in prod and circumvent it pretty often that ways. All right, so now we'll jump into the certificate extension PKI issue. This is the kind of spicy one. So a little bit of background for anyone who isn't familiar with certificate extension. Specifically, we're going to be talking about the basic constraints and key usage extensions, more so the basic constraints extension. But first, we'll talk through, we'll do a little jump in our time machine, go back to 2009 and talk about SSL strip, if anyone's ever used it. So back at Black Hat 2009, actually, Moxie gave a talk called New Tricks for Defeating SSL in Practice. And at the time, his research had found that the common browsers weren't actually validating the basic constraints extension, and any person who had a valid SSL certificate, like you're just literally running a site, like you own a domain and you got a SSL certificate, you can literally just take like the key file that you got from your CA and create a new leaf certificate claiming that you were a different domain and sign it, and modern browsers at that time in 2009 wouldn't throw like an untrusted site error, right? So if you ever used SSL strip, this was a really common technique for defeating SSL back in the day. You could like phish someone, say that you are eBay, and set up like a credential harvesting domain. Yeah. So how did that work? This is the basic constraints extension problem. So if you look at the RFC, the basic constraints extension basically has two parameters. There's a certificate authority parameter, which it's a Boolean, true or false. If true, a certificate authority means you can mint child certificates. If false, you can't. And then there's a path length constraint, which is actually optional, but it will actually define the depth of the chain. So this is just defense in depth techniques basically for making sure that X509 certificate chains are valid. So what you would hope is that like a leaf certificate in a legitimate chain, the CA would be set to false. Or sometimes they don't include it at all, and it's supposed to default to false, meaning you can't extend the chain basically. And here's an example of what a legitimate intermediate cert looks decoded in Android key attestation implementation. So how do you test for this in the Android ecosystem? So this is where things are a little bit more unique, because within the browser example that I mentioned and like how SSL strip works, very easy, right? You can assume that you have a key file on file system that you can use to basically craft and forge an entire certificate chain. Little different in Android, because the key pair and certificate chain are in the Keystore, so we can't actually get our hands on it. So what we have to do to test this is we have to write an Android app, essentially. We have to actually use the Keystore API, and what the steps kind of look like, and walk through it a little bit more in the following slide. But you'll basically create an insecure EC key pair. So you'll just like store it in memory, not in the Keystore. You'll build a X509 leaf certificate, and embed the public key, do all the same steps that we mentioned previously. But one of the unique things is we're actually going to use the Keystore API to use a legitimate key pair to sign it and extend the certificate chain on the device and then exfiltrate it off the device. And this should fail if we're doing a proper certificate extension check, because what it would look like on the backend validator is it would see that the legitimate leaf certificate in the chain should not be a certificate authority, and it can't sign and actually extend the chain farther. But yeah, so we'll dive into that really quick. And one of the ways that I was able to POC this was actually using a really popular Android key attestation debugging app that's out there on GitHub. I'll release all the references to this at the end, but you can actually debug. It's for like the custom ROM community to make sure that your custom ROM can actually get past legitimate Android key attestation checks. But you can build a bunch of interesting app code, basically, again, small font, but also releasing a tool that's going to have all this information in it. But really what we're doing here is generating a leaf certificate. We're going to use the Keystore API to pass it in, sign it, and then we're just going to exfiltrate it off the device by printing it to standard out, and we'll pull it out. And then you can just orchestrate your testing similar to what I mentioned before, where really what the backend server is expecting is you to send a chain to them anyway, so you just need to get all of the X509 certificate certs, and you can send them in a post request to the backend. And what you can see here is that this actually worked on our research target. We got a valid key back, and we're able to interface with the app off device, like literally just like Python scripts on a local computer. Root cause analysis of why this worked. I'll caveat this in saying that this root cause analysis was done last year in 2024. I will have a follow-up disclosure timeline coming up shortly, but just a frame for context. So what we found when looking at this is the target, our research target was actually using the Android key attestation library, which is in the documentation. And it basically guides developers to use this library. So at first, we're like, this is interesting. Is this going to be an issue in the library? And kind of diving into what we found was it was released in 2016, tagged as a production library, maintained in parity with the developer documentation. And there's a screenshot here that has the actual documentation from like the Android key attestation documentation. And one of the really interesting parts was it literally called out a caution about certificate extension attacks. So one would think the library would defend against those naturally. So natural first thing to do was to start digging into the library. And what we found, this is the README off GitHub. And again, like this is saying, this is maintained in tandem with Android key attestation's capabilities, and it is meant for production use. So we dove into the library server code, and what you can see is the library is really doing two main things. First, it's verifying a certificate chain, as one would expect. That's part of the common practice of validating any X509 certificate chain. And when we looked at the code on the right, that's the actual verifying certificate chain checks. Everything looked good. It looked like it was doing what it was supposed to. So kind of strange that this worked. And then you can see on the screenshot on the left, the second arrow is after the chain's validated, it's doing what it's supposed to. It's parsing the custom attestation off of the OID extension. Everything looks normal. If you dive into the actual attestation parsing code, you can see that there's also even a comment block specifically warning about certificate chain extension attacks. So again, you're like, why is this working? This should not have worked. Well, when we diffed our research targets code and the library code, what we found was they were different. So you can see on the left here, the create parsed attestation record method is actually expecting just to be passed the leaf certificate, really saying that the developer should have already validated the X509 certificate chain. Whereas the latest code on the right in the library was taking the whole chain and had that built-in protection where it was actually parsing from root to Leaf and taking the first attestation there, which is kind of a hacky way, but still a way basically of making sure that they're not going to be parsing any like attestations that were tacked on in successive Leaf certificates. So here we're thinking, well, this is weird. Like maybe, so it was a vuln that was patched, like, but maybe we didn't patch the CVE in our research target. So we diffed the fix in GitHub and found that there was no CVE. So they mitigated the attack, and we never got any notification that the CVE existed in the first place for us to go through and patch it. And if anyone works at a large company that has your own custom build system, like this is one of the things you rely on to make sure that your internal mirrors are up to date with the external repositories. Which, speaking of, our next thought was, well, there's no CVE. That's still cool. Why aren't we on the latest? Like, why aren't we on main? Like, why is our internal mirror not on the main branch? Well, come to find out, they didn't do any formal releases, and the package is not published to any central repository. So there is no way to keep up with main unless you are manually going to GitHub every day and checking to see if someone's pushed a new commit. So here already we're like, okay, red flags, red flags. Like I thought this was a production library. How are we here? How did this happen? So we go back to the developers. They update our internal version of the library, and we test again, and it still worked. So now we're just like so confused. Like how? So we dove into the code, the final patch that claimed to have fixed the problem. And what we can actually see here is the library itself isn't following best practice. It's not actually doing certificate chain validation. They did a sort of like hacky workaround for trying to circumvent certificate extension attacks. They're not actually checking the basic constraints and key usage extensions. They're basically assuming that every developer is passing the certificate chains with Leaf first ordering into the method and using an ordering-based approach to parse out the first Leaf certificate in the chain, which generally is a safe assumption because the get certificate chain method that is in the Keystore API does produce a Leaf first certificate chain. And this is also general best practice if anyone's ever done anything with like was it PKIX libraries in Java. Like this is common practice. But Android and developers and Murphy's Law, our implementation that we looked at, as well as a few others, we're doing root first ordering. And we have found this to be an effective bypass technique. There's two really interesting ways. One is the developer does root first ordering with their certificate chain validation, which is a completely implicitly fail open scenario where you're always going to be able to basically exploit this. And then the other really interesting one is when they do an ordering based approach to certificate chain validation, because you are the client passing the certificate chain to the backend, you control the ordering of the chain. So one of the really funny ways to test this is you can literally just take your chain and flip the certificates to flip them to root first instead of Leaf first ordering. So disclosure timeline. This is kind of what everything looks like, and this is current day. So in December 2016, Key Attestation Library was published to GitHub. And Google Android was like, yeah, it's production. Send it, use it. In 2023, they patched that certificate extension attack without a CVE that I just mentioned. In September of last year, 2024, I reported the 3 issues that I mentioned to them. And then 2 months later, they said, we won't fix this because we are going to deprecate this. We were like, OK, sounds good. And then they closed out the ticket, didn't hear anything back. And then at the end of November, they finally updated the README and said, Not intended for production use anymore. I was gonna put a bunch of screenshots from Wayback Machine in there, but if anyone's interested, it's kind of funny to just diff the commits. You can just like actively see the development stream of like, all right, well, let's remove all liability, and we'll just start by saying you can't use this in production anymore. And then in April of this year, so about 4 months ago, they released the new version. Still have not updated any documentation or anything in the README of the first library. And then as of June, they finally updated the README, locked the repo to read-only, and said there's like a new comment that says, this is now deprecated, go use this one. But as an external developer who's trying to implement Android key attestation, what you actually see is you go to the Google Docs, and they tell you, implement Android key attestation, you click on the library, it takes you to a deprecated library, then in the README you have to find another link that then takes you to another library that is actually also still actively being developed right now. It's like in progress. So yeah, that's the current state. So to wrap everything up and really like unpack that disclosure timeline, first off, what we see is right now Android key attestation is in a fragmented state. So if you look at that disclosure timeline, what we really see here is if you implemented Android key attestation from 2016 to 2023, you are implicitly vulnerable to a certificate extension attack if you use the library that the developer guidance tells you to. If you implemented key attestation post 2023, you might be fixed maybe. It just depends on if you did your due diligence with the way that you're doing your certificate chain parsing and validation. And then if you're a developer about to go implement it, hopefully you use the new library that's also not completely done being developed, but also good luck. One of the other kind of takeaways here is during this research and diving into like all the techniques to circumvent this, what I found was there's a well-organized and concerted effort to circumvent key attestation online. It's actually very interesting, both from the like real, what I'll call like threat actor or adversary that is continually poking at all implementations, the library. There's lots of discussions. There's some really interesting Telegram chats about like folks are basically trying to pay researchers who find vulnerabilities in trusted execution environment to not disclose and continually pull compromised key boxes off of legitimate implementations. But like all of those like well-organized communities, they continually get burned. It's kind of interesting. It's a kind of an interesting like threat intel angle to look at. And then I will say, though, fragmented environment aside, if you are doing proper X509 certificate chain validation and rolling your own attestation parsing, and also there's some good libraries out there, like the WebAuthN 4J is like a pretty well battle-tested library that supports all attestation types outside of just Android. Highly recommend looking into that one. It is an effective mechanism for combating bot fraud and abuse. A really cool metric that we got out of this after working with our research target and they fixed everything was they actually saw bot traffic drop from 30% to 2%. And it's been holding pretty solid right at that level since then. And final thing is go test your own implementations with Key Attester. So I'm releasing a library. I'm going to open it up as soon as I get off the stage here. But it'll basically build custom X509 certificate chain payloads to test all implementations. This is going to go over all the cases that I've mentioned today and the ant code that I had up here. Don't worry about trying to copy that. It's going to be on my GitHub. So if you're a developer who is actively has like their own implementation or looking to, please use it, include it in your unit tests, make sure that you're validating chains right. If you're a OffSec engineer, pen tester, what have you, have fun. Hopefully you find something cool out there. Thank you. Do we have time for questions? Do we have time for questions? I don't know, 2 minutes.
Yeah, we've got about 2 minutes for Q&A if we've got some mics up here if you guys want to line up and ask some questions.
Thanks. Yeah.
So wild response from Google there. Did you try filing a CVE retrospectively to say like, hey, this version's still thing?
Yes. So one of the things I left out because time was we actually submitted 3 different times. And funny enough, if anyone was in the talk just before mine, we got the same response they did from Apple, from Google, where it was, this isn't an Android problem because this is an Android source code, so that's not our problem. And then we submitted it to the open source VRP, and they were like, this is an Android problem. And it was like this awkward punting back and forth for months. And the third and final one that we finally got to take in, we like implored them, hey, cool, don't fix this, but like, can you at least issue a CVE for the former? And they said that they didn't feel that it warranted the severity to release a CVE.
Good talk. Cool. Cool.
Thank you.
I would be selfish if no one else got anything.
Yeah.
So you said that, all right, there's the GitHub that said, hey, this isn't a prod library, but all of their documentation said use this library. If not that, what should people have been using? Or is this a generic cop-out of liability if there is no prod library?
Yeah, I think there was a cop-out of liability. So there is a new library that's out there now that also claims to be for production use. Can't like confirm the efficacy of that one. So give that one a shot and check it out. But I'll say one of the solutions that we ended up with was really like rolling our own crypto. It was basically like using a PKIX, like Java built-ins to do X509 certificate chain validation. And then the WebAuthN for J library that I mentioned is a really good, like it's a I won't say funded, supported open source project that has a bunch of really cool work for all types of device attestation. It actually does FIDO2 and WebAuthN stuff too for any organizations that are doing anything like that. So I would recommend taking that approach. Like, shame to say, like, roll your own crypto. Like, don't, like, I won't trademark that. But unfortunately, like, with the current state of what libraries are out there, it's just not really great. But there's also a confusing thing too, because the library itself actually claims to only do attestation extension parsing. It doesn't claim to do X509 certificate chain validation, but they included it. So it's a weird, like, guilty by association thing where it's like, do as I say, not as I do. Like, you can't include an example of doing the validation and not expect a developer who you pointed to the library to basically take your code.
Gotcha. All right, I appreciate it. Thank you.
Yeah, thank you for the question. All right, good guy.